Welcome to G Fun Facts Online. Look at any major city skyline today, and you'll see buildings that don't just reach up, they reach out. Massive sections of skyscrapers hang in mid-air, seemingly defying gravity. These are cantilevers, and they're one of the most daring and brilliant feats of modern engineering. They allow architects to create breathtaking forms, vast open spaces, and push the very limits of what we believe is possible in construction. Today, we're pulling back the curtain on the physics, the history, and the incredible technology that allows these gravity-defying structures to reshape our world. So what exactly is a cantilever? At its heart, it's a surprisingly simple idea, a rigid structural element, like a beam or a slab, that's anchored at only one end. The other end is free. To get a feel for this, try a little experiment. Hold a heavy book in your hand with your arms stretched straight out. Your shoulder acts as the fixed anchor point, and your arm is the cantilever. You can immediately feel the forces at play. You feel tension in the muscles on the top of your arm, which are being pulled apart, and you feel compression in the muscles on the underside of your arm, which are being squeezed together. A cantilever beam in a building experiences these exact same forces. The upper half is under tensile stress, being pulled apart, while the lower half is under compressive stress, being squeezed. The cantilever's strength comes from the material's ability to resist these two opposing forces simultaneously. The success of a cantilever depends on three main things: the depth of the beam, the weight it has to carry, and the material it's made from. Deeper beams are much better at resisting bending, and modern materials like steel and reinforced concrete have immense strength against both tension and compression, making long, heavily loaded cantilevers possible. This idea, however, is not a modern invention. The concept has been used for centuries. In traditional Chinese architecture, intricate wooden bracket systems known as dugong were used to support the wide, overhanging eaves of temples and palaces. Ancient Greek and Roman builders also used cantilevered balconies and eaves for both shade and decoration. But for most of history, the potential of the cantilever was limited by the materials available. Wood and stone can only extend so far. The true game changer was the Industrial Revolution and the mass production of steel. In the late 19th century, engineers began building massive steel cantilever bridges that could span vast distances without needing supports in the middle. The pivotal moment came in 1890 with the completion of the Forth Bridge in Scotland. This iconic structure, with its three enormous diamond-shaped cantilever towers, was a monumental demonstration of steel's potential. It showed the world what was possible and paved the way for cantilevers to move from bridges into buildings. The architect who truly pioneered the cantilever in residential architecture was the visionary Frank Lloyd Wright. His 1906 Roby house in Chicago featured a dramatic cantilevered roof that extended an incredible 20 feet beyond its supports, creating a sense of lightness that was revolutionary. But his masterpiece is Fallingwater, completed in 1937. Its iconic concrete terraces are cantilevered directly over a waterfall, appearing to float effortlessly in the landscape. These early examples, made possible by combining steel and reinforced concrete, showcased the sheer beauty and spatial possibilities of the cantilever, setting the stage for its use in modern skyscrapers. In the dense urban landscapes of the 21st century, the cantilever has become an indispensable tool. In space-starved cities like New York, it allows architects to extend floors out over neighboring buildings or open public spaces, maximizing usable floor area. So how do engineers support these immense, gravity-defying structures? One common method is to use a strong central core. This core, typically made of reinforced concrete and containing elevators, stairs, and service shafts, acts as the building's massive spine. The cantilevered floors then extend outwards from this central anchor. To enhance stability, especially against powerful forces like wind or earthquakes, engineers often use outrigger systems. Think of a skier using their poles for balance. Outriggers are stiff horizontal structures, like trusses, that connect the central core to the building's outer perimeter columns. This connection engages the entire building frame, making it vastly stiffer and reducing the bending stress on the core. For the longest and most heavily loaded cantilevers, steel trusses are the go-to solution. These are complex, three-dimensional frameworks of interconnected steel elements that can be as deep as a full story of the building, providing immense strength. Another innovative solution is the diagrid, a diagonal grid of steel that forms a strong, rigid, tube-like structure around the building. It's incredibly efficient at handling both vertical and lateral loads and creates beautiful, column-free interiors. Now for the most exciting part, let's look at some real-world examples that are pushing the limits of what's possible. First, let's go to Dubai, a city of architectural superlatives and home to the world's longest cantilever. The One Zaabeel development features a breathtaking 230-meter-long horizontal sky bridge, known as the Link, that connects its two towers. The jaw-dropping feature is its 67.5-meter cantilever that projects out over a 6-lane highway, hanging 100 meters in the air. The engineering was simply monumental. The Link, which weighs over 9,000 tons, was constructed in segments on the ground and then lifted into place in one of the most complex crane operations ever undertaken. To accommodate the immense weight of the bridge, the two towers were intentionally built with a slight lean towards each other. Once the Link was attached, its weight pulled the towers into a perfectly vertical position. Its structural integrity is ensured by a powerful diagrid system, creating a strong, torsion-resistant tube. Before One Zaabeel claimed the title, the world's longest cantilever belonged to the iconic Marina Bay Sands in Singapore. This resort is famous for its three 55-story hotel towers connected by a 340-meter-long sky park. Nearly 200 meters above the ground, this park features a 65-meter cantilevered observation deck, offering panoramic views of the city. A major engineering challenge here was the famous infinity pool that runs along the top of the sky park. To maintain the perfectly level edge required for the infinity effect, engineers had to account for the natural sway of the towers in the wind. Their solution was to install a system of 500 hydraulic jacks beneath the pool basin. These jacks constantly make micro-adjustments to compensate for the tower's movement, keeping the water's edge perfectly still. Now let's travel to New York City's Tribeca neighborhood to 56 Leonard Street, a skyscraper affectionately nicknamed the Jenga Tower. Designed by the firm Herzog & de Meuron, the building is a dramatic stack of irregular, cantilevered glass boxes, creating a pixelated effect against the skyline. The cantilevers range from 10 to 25 feet, meaning almost every one of the 145 apartments has a unique floor plan and an outdoor space. This seemingly random arrangement was a huge structural puzzle. The engineering team developed a solution that used a strong concrete core linked to external columns by outriggers. For the smaller cantilevers, simply making the concrete floor slabs thicker provided enough support. For the larger projections, they incorporated additional hidden beams. And for the most extreme cantilevers, they used a special kind of frame called a Vierendeel truss, which engages two floors to provide support without obstructing the interior space with columns. The tower is also equipped with a slosh damper, a large tank of water at the top of the building, which sloshes in the opposite direction of wind-induced movement to keep the tower stable. The design of these complex skyscrapers would be impossible without advanced computational tools. Structural engineers rely on sophisticated software like ETABS and SAP 2000 to create detailed 3D models. They can then subject these virtual buildings to a huge range of forces, gravity, wind, earthquakes, to analyze stresses and ensure the structure is safe and efficient. One of the biggest challenges is wind. For this, engineers use computational fluid dynamics, or CFD. This software simulates the flow of air around a building, allowing them to predict wind pressures and design the building's shape to be more aerodynamic. All of this is coordinated using Building Information Modeling, or BIM. This allows architects, engineers, and contractors to all work on a single, integrated 3D model, reducing errors and making the entire construction process more efficient. So what does the future hold for cantilever engineering? As cities continue to grow, the demand for innovative skyscrapers will only increase. We can expect to see even longer and more audacious cantilevers, thanks to advances in materials like ultra-high-strength concrete and lightweight carbon fiber composites. We're also moving towards smart and responsive structures. Imagine buildings with integrated sensors that monitor their own health in real time and actively adapt to environmental conditions, using smart systems to dampen vibrations. The trend of integrating green spaces, like the Sky Park at Marina Bay Sands, will also continue, with cantilevers providing unique opportunities for elevated parks and gardens that bring nature into the urban core. Cantilever engineering is more than just a structural technique. It's a form of architectural expression that creates buildings that are both highly functional and breathtakingly beautiful. From ancient temples to the super-tall skyscrapers of tomorrow, the cantilever continues to capture our imagination, forever changing our relationship with the vertical world. Thanks for listening to Fun Facts Online.